Okay, so this is a study guide for exam 4, so about that, for organic 1 in the spring of 2016, so about that. So okay, so we'll go ahead. So there's going to be a couple of compounds, so this is obviously the free answer part, like all the other ones, right? So we're going to be giving a couple compounds, you got to name them, so about that. So just don't forget that the halides don't get any sort of special special consideration, stuff like that. So for these compounds here, we're going to name them like regular alkanes, regular cycloalkanes. Okay, so here we go. So you got to check the put in your dots as needed. So okay, so about that. So here we go. So find the longest chain, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yeah, so like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it looks like you've got two different chains that are 9. I'm gonna pick the horizontal one but it doesn't matter. It'll give the same results. Okay, so we have our side chains, right? So main chain is right C9, so that would be nonane, right? Okay, so like that. So we have so we have that methyl group there. Right, we have that bromine there, so it would be bromo, right? And then this 2 carbon piece here, which would be ethyl. Okay, so if we're going to do, right, so then we have to check to see which way the main chain is going to go, right? So we go from the left, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So about that. So in this case, the methyl will be at 6, bromo's at 5, ethyl's at 3. Right, but if we do the other way, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, right, so that ethyl group would be at 7, this one would be again at 5, this one would be at 4, right, so we're going to add them up, right, so 11, this would be 14, right, so 11, that would be 16, right, so we're going to use those numberings there, okay, so, right, so we have to next go alphabetically, right? So you check the bromo, ethyl, methyl, right? So bromo comes first alphabetically, so it ends up being 5 bromo, right? So ethyl comes next, so 3 ethyl. Let's use 6 methyl, nonane. There we go. Okay. All right. So for this one, all right. So with that, so you can always mark in your carbons, right? So put in your dots. Okay, so here's a long straight chain. Remember with this, right? You can either have straight chain or ring, but you can't have both, right? You can't be both. It's either one or the other, right? So for straight chain, right? 1, 2, 3. That's the longest. For the ring, it's 1, 2, 3, 4, 5, 6. Okay, so right. So this is going to be our main chain, right? So it's C6. It would be hexane, right? But to indicate that it's a ring, it would be cyclohexane. Okay. Now we've got, right, so that's a propyl group, right, but, right, so it's 1, 2, 3 long, right, but since it's connected to the main chain through carbon 2, it's a 2-propyl group. Okay, so this is methyl, and this is chloro. Okay, so we're going to make each one of these 1 and see how the numbering comes out, right? So if this is 1 here, we're going to go towards the nearest side chain neighbor, so 1, 2, 3, 4, 5, 6, right? So this would be 1, 3, 4, right? So if we're going to make this one 1, right? So the nearest side chain neighbor is here, so 1, 2, 3, 4, 5, 6, right? So with that, so 1, 2, 5, right? So with that, so, and then the last one is to make this one 1. Now this one we're going to go counterclockwise, right? Because the nearest side chain neighbor is here. So 1, 2, 3, 4, 5, 6, right? So this becomes 1, 2, 4, right? So we're going to add them up. So this is 8, this is 8, this is 7, right? So we're going to use those numbers there. So it becomes, right? So in this case, right, chloromethylpropyl. Okay, so here we go. So there's 1 chloro. Methyl is next, so it's 2 methyl. Okay, so there's 4 2-propyl, right? Cyclohexane. Okay, so we have a 2-propyl group. Where is it connecting to the main chain? Into carbon 4. into carbon 4 if we use those red numbers. So there's your name. So, okay, so for these, right, so reactions to know, right, so with that, so, right, so for this one here, right, so for MBS, right, so you're going to add it to what's called the allylic position, which is the carbon next to the double bond, right, so here's the double bond here, so you're going to add it either here or here. So as long as there's one hydrogen, there's one carbon-hydrogen bond on that allylic position, you're good to go. So, right, so if you can add it there, which put it there, on this carbon here, which makes this compound, or you can add it, right, this is eligible here, right, that's allylic, so you can put it there. Okay, so for tertiary alcohols, right, so with that, so you can interconvert them into, convert to, in the corresponding halides if you just do HF, HCl, HBr, HI. No problem. So with that. Now, if it's anything other than a tertiary, you're going to definitely have to use this. So this would also work with tertiary compounds, right? So thionyl chloride, right, converts an OH into a Cl. PBr3, right, converts an OH into a Br. HF pyridine is going to convert an OH into the corresponding fluorine, right? So if it's just so for this case, right, if it's a tertiary alcohol, you can just use regular HF. But if it's a secondary tertiary alcohol, you're definitely going to need that pyridine in there. So about that. So so reactions to know. So about that. So more reactions to know. Right. So for here, right. So about that. So for magnesium, it's going to insert between the carbon and the bromine. Here, lithium just swaps for the bromine. Okay. Because remember, this carbon here has a -1 charge. The magnesium typically has a +2 charge, so that means we're going to need to keep that bromine around because that's going to have the negative charge. But for here, right, that carbon is a -1, so with that, but the lithium that has a +1, so everything's balanced out. Okay, so again, you're going to have this carbon here, which has a negative charge, right? So that this carbon here, right, that has it's going to be positive character, right? Because the bromine's going to have negative character, so you're going to have attack there, which kicks this away. So you're going to make a new bond between where the magnesium is attached and where this bromine was attached. Okay. Same thing here with you're going to make a new bond between here and here, right? You're going to make a new bond there. And for here, what you're going to do is, where one of these groups, you only add one, is attached to the copper. So this one here, that's going to make the new bond there where this bromine was. So they all work the same way. So now for this one, again, instead of having one of these guys here, it's going to be where this boronic acid is attached. That's going to make a new bond where this bromine is. Okay, these other groups don't really matter much. But you're going to make a new bond between here and here. So this is the Suzuki coupling. Okay. Okay, so here we go. So thionyl chloride, its whole purpose in life is to turn OHs into Cls. That's all this is. Now for here, right, so you have that. This is a negative charge, right, because it's +2 -1, right, like that. So here, this carbon, right, is going to have positive character because the bromine's electronegative, right, so it's going to be sucking electron density down to here, right, so so this is going to get attracted there. It's going to kick away the bromine, so you're going to end up with that. Okay, where that magnesium is attached, it's going to be connected where this bromine was. Same thing here, right? So this 3 carbon piece here, right? So this carbon is going to want to make a new bond where that bromine was, right? So it's going to get kicked away. So you're going to end up with this O-methyl group here doesn't matter, right? So you're going to add this 3 carbon piece. 1, 2, 3, this 3 carbon piece where that bromine was. Okay. There you go. Okay, so preparing alkyl halides from the alcohols, right? So if you're going to have, so keep this simple. Okay, so here you're going to add, I don't know, HCl. Right? Cl plus H2O. Okay, so I'm going to give you this. You got to tell me what the curved air mechanism is. Okay, so the way this works is, right, so don't forget this has positive character, this has negative, right, so it's a polar covalent bond. these electrons here are going to get attracted to that hydrogen, and then since we're making a new bond between a new oxygen-hydrogen bond here, you're going to make a new bond to this hydrogen. It doesn't need those, right? Because hydrogen only needs the one electron, or one bond, right? So it's going to push those electrons onto that chlorine to make this, right? So this second hydrogen here is just coming from the HCl, but that results in a positive charge here and a positive formal charge on that oxygen, right? And then the chlorine's going to come out. Since it has a new set of new lone pair, it's going to have a formal negative charge. Now this guy here, right? When we mark these carbons here, it's a little bit easier to see. This is going to get pushed away. Strip this apart to make right, HOH, right? Right, make water, right? And then this, just these 3 carbon pieces. But now this guy here is going to have a positive charge, right? So with that, so this is going to get attracted there, right? To make that. No worries. So with that, so they're all going to work exactly the same way. This is probably not so great because you have a primary alcohol, but again, it doesn't really much matter. Stuff like that. So the mechanism all works the same way. So, okay, so for oxidation and reduction, okay, so what you're looking for is, right, so carbon electronegative, negative bonds, okay, bonds, right, plus carbon-carbon pi bonds. Okay, right. So if you have a so a carbon-carbon bond, right. So if you have pi bonds, sigma bonds, right. So this is going to have one sigma bond, right, and 0 pi bonds. A carbon-carbon double bond, right, has 1 sigma, right. That's the first one that always gets laid down. But then each additional one is going to be a pi bond. So this has 1. So carbon-carbon triple bond, right, it has 1 sigma bond and 2 pi bonds. Okay. So you're going to see if it goes up, right? So if the number goes up, it's going to be an oxidation. If it goes down, it's going to be a reduction. If it stays the same, there's no redox. Okay, so for here, so for this one here, right, we have no carbon electronegative bonds. Okay, and then we're going to add to it, right? So how many pi bonds here, right? So it has 1 sigma 1 pi bond, so it'd be 1, right? So it'd be 0 plus 1, so 1. Now for this side, right, so we have 2 carbon electronegative bonds, right, but since this double bond's gone away, we don't have any additional carbon-carbon pi bonds, right, so we're going from 1 to 2, since the number's going up, this is an oxidation. Okay. Now for this one here, right, there's actually 3 carbon oxygen carbon electronegative bonds, right? So we have 2 carbon oxygen bonds here, right? So 1, 2, and then we also have 1 here. Okay, so 1, 2, 3. Okay, no carbon oxygen pi bonds, right? So with that, so 3. So for here we only have the 1 carbon electronegative bonds here, right? So it's just this one here. Okay, and again, no carbon-carbon pi bonds, right? So the number goes from 3 to 1. Since the number's reduced, this is a reduction. Okay, so for this one here, right, we don't have any carbon electronegative bonds, but we do have 2 pi bonds here, right? So we have, right, a triple bond is 1 pi bond and 1 sigma bond and 2 pi bonds, right? So with that, so it's 2. Okay, now for this one here, right, so we have 2 carbon electronegative bonds, right? So 1, 2 carbon oxygen bonds, right? So with that plus no pi bonds, no carbon-carbon pi bonds, right? So 2 to 2, right? So we're going from 2 to 2, so that means that there's no redox, no overall redox. Okay. Okay, now for this one, I'm not going to give you this part, but I'm going to give you this sort of bottom part on the on your equation sheet, so you'll have access to this. Okay, so there's going to be 2 parts to this, right? So to do the name, right? So first, you're going to need to know if it's an aldehyde or a ketone. So So for this one here, right, it's a ketone, right, because there's carbons on either side of that C double bond O, right? So when it's a ketone, right, we say that it's a keto sugar, so it's a keto. Next thing you're going to do is you're going to have to figure out how many carbons there are. So 1, 2, 3, 4, 5, 6, 7, right? Stuff like that. So, right, don't forget that there's a carbon underneath here. Okay, so since there's 7, it's a heptose, so it's a keto heptose. Okay, so this part mean that there's a ketone in it. This part's saying that there's 7 sugars in there, right? So it needs to be a keto heptose. Okay, so for this one, right, so here, because there's an aldehyde here, so C double bond O with an H coming off of it. So the presence of that H actually is a dead giveaway that there's an aldehyde. So with an aldo sugar, why don't we say it's an aldo? Okay, now count the carbons, right? So 1, 2, 3, 4, 5, 6. Now don't count that hydrogen, that's a hydrogen. We're just counting carbons. Right, so we come down here, so a 6 carbon sugar is a hexose. So it's an aldo hexose. Okay, so like that. So there you go. Okay, now for this one, all we're looking at is the, it's usually this carbon here. It's the last chiral carbon. Okay, so it's actually this one here. So for D's, if it's pointed that way, it'll be a D. If it's pointed that way, the OH is pointed that way to left, it's an L. Right, so that's all you gotta look at. It's just this one here. So this one's pointed. This one here is pointed to the left, so it's D. Okay, this one here is pointing to pointing to the right. So this one here is pointing to the left, so it's L. Okay, for this one here, this one is pointed to the left or to the right, so it's D. Okay, notice how these guys are pointed left, doesn't matter. These guys are pointed each different ways, doesn't matter. This one's pointed to the right, doesn't matter. It's just this one here. Now for a cyclic sugar, right? So what you're looking for is actually, so let's say this one here, it's the presence of the CH2. Okay, if it's above the ring, it's D. If it's below the ring, it's L. Okay, so if I had this, okay, so we have ribose here. Okay, notice how this here, right? So on this carbon here, there's 2 bonds shown, right? So that means that there's a CH2 there, right? So you're looking at that one right there. This is above the ring, right? So that makes this D. Okay, so if you're going to have this be below the ring, right? Oops. OH like this. This CH2 here, right? There's 2 bonds shown, right? There's 2 bonds shown, so it means it's CH2 there. Even though this OH is pointed up, the CH2 is below this ring, so this one would be an L. Okay. Okay, so for the L form, right? So you're going to make the L form of the sugar, right? So this is D-lixose, okay, and this is D-xylose, okay. I want to form the L, not an L sugar, but just an L form of the sugar. Okay, so what I'm really asking for is to draw L-lixose, and to do that, you're really just interested in those OHs there, the middle ones. Okay, those are the chiral ones, and what you end up having to do, okay, so the outer ones, this one in here doesn't matter. Right, so this is right, or this is left, right. So you're going to do the mirror image. So you need to have this right, left, right. And we know it's an L sugar, right, because that guy there is pointed that way. Okay, so this is what I'm interested in. There. Again, for this one here, I'm just interested in that part. Okay, so we're going to make L-xylose, which would be, you keep these guys the same because those aren't chiral, but here, right, so this is right, left, right. Okay, so we'll draw the mirror image. So there we go. So this would be the L-xylose. This would be the L-lixose. But this is what I'm interested in here. Okay. Okay, so for the Kiliani-Smith reaction, right? So so what you're doing is you're extending the chain one additional carbon, okay, at the top. Okay, but when you do that, the aldehyde, half the time it goes on one side, the other half it goes on the other. Okay, so you find, so here's L-arabinose here, or excuse me, D-arabinose. Okay, so it looks like this. Okay, and so when you go through, so this is D-arabinose. Okay, when you extend it out, you're really just interested in this and that one there. Okay, all the rest of this bottom part's going to be the same. Okay, so what ends up happening is, okay, half the time this OH is going to go here, right? We're going to extend it out one more, right? So that we're just interested in here, right? So 1, 2, 3, 4, 5 from the top. 1, 2, 3, 4, 5 from the top. Half the time it's going to be here. The other half, the time it's going to be the other way. Okay, so we're going to make these two sugars. Okay, so these are the same carbons. Okay, so this one here, that is, you kind of, I'll give you this chart down here, right? So that is this one here, so D-glucose. Okay, the other one, right, left, left, right, right. So would be this one here, left, left, right, right. So this would be D-mannose. So you're going to have to draw the sugars and then go back to this chart and figure out what they are. Okay, so from D-arabinose, if you do a Kiliani-Smith, you're going to make D-glucose, D-mannose. Okay, so for a wool degradation, okay, so you're going to take D-galactose, which is here, here. Okay, what you're going to do is you're going to end up removing that carbon, so it's a degradation, right? So we're going to remove the top carbon, and we're going to make that into the aldehyde. Okay, so this is originally D-galactose, but what you end up getting is this. Right, so this carbon here is this carbon here, right? So we're just lopping off the top and making this the new aldehyde. Okay, so left, left, right, right. So that's left, left, right, right. So this is D-lixose. Okay. Okay, so for these, okay, so you have to remember, so it always goes, right, so it always goes left to right. Left sugar versus right sugar, right? And alpha goes down, beta goes up relative to the left-hand sugar. Okay, so the number of these things, right? So you have a 6-membered ring here, right? So that means you're going to have a 6 carbon sugar, right? So if you want to mark in your carbons, you can, right? Don't forget that there's a carbon there. Don't forget there's a carbon there. Okay, so the one that's out is going to be the last one. It's going to be your last carbon. So this is going to be 6. It's a 6-membered ring. That means I have a 6 carbon sugar, right? So 6, 5, 4, 3, 2, 1. Now it gets a little more complicated if it's a keto sugar. I'm only going to give you aldo sugars. Okay, so like, same thing here, right? So 6, 5, 4, 3, 2, 1. Same thing here, right? 6-membered ring. So that means this is 6, 5, 4, 3, 2, 1. Again, this one here, right? The 6-membered ring. So that means this is 6, 5, 4, 3, 2, 1. Now, if you get to here, right? If you get to this carbon and you're not at 1, something's gone wrong. Okay, that oxygen doesn't count, right? We're just counting carbons, right? So if you get here 6, 5, 4, 3, 2, that means you've done something wrong. You've forgotten about this one, or you've started here 6, 5, 4, 3, 2. You've missed this one. Okay, so if you get to this point and you've messed up, you've probably missed one of these two. Okay, so with that, so okay, so we're always going to left to right. So with that, so we're, for this first one, we're only interested in these two. This is the left-hand sugar, right? So we're interested in this linkage here, right? So it's going down relative to the left-hand sugar. So that means it makes it alpha. okay? And you're going from carbon 1 here, right? That's carbon 1 to carbon 6 over here. So it's an alpha 1, 6. So for this one here, right? So this is the left-hand sugar, this is the right-hand sugar, right? So for here, right, the linkage from the left-hand sugar is going up, so it's beta, right? And you're going from 1 to 4. Carbon 1 on this side to carbon 4 on this side. Okay, now on this one here, right, so just take these in isolation, right? So this is the left-hand sugar now, right? Because notice how this ring is slightly shifted relative to this one. Okay, so this is left-hand sugar, right? So this is so from left-hand sugar, the linkage is going down, so it's alpha, stuff like that. So alpha 2 to 6, going from carbon 2 to carbon 6. Okay, so there you go. Okay, reactions to know. Okay, so just know that if you have your sugar, I'll be presenting them like this. If you have an aldehyde here, right, for sodium borohydride, it reduces it down to the alcohol. Now for these guys, the CO2H, these are carboxylic acids, right? So like that. So for bromine, you just do you convert the one at the top, so the aldehyde, to the carboxylic acid. With an enzyme, you can actually do the bottom, right? So the last carbon, make that into a carboxylic acid. But if you do nitric acid and heat, you can actually convert both ends, the top and the bottom, to carboxylic acids. So get working on the homework and let me know if you have any questions. Thanks.